Okay, so last class we ended with this acetoacetic ester synthesis. I just want to remind you because,
Are you going to give us the beginning products and the end and maybe show the mechanism?
today, no mechanism, no mechanism. It's all just, you'll find it really easy, just aromatic substitution reactions. Reagents, product, reagents, product, reagents, product.
We just have to say the reagents and products.
No, I'm giving you the reagents and the reactants. You just have to show me the product of the reactions. That's it for today. So, and it's the first one, I'll tell you right now, the first question is, we did 5 aromatic substitution reactions. That's the first question, is those 5 reactions. So you just have to be able to put on what's on the ring, okay? And then the second one is directing.
Like arrows?
No, like directing groups, either meta or orthopara directing. So you'll have to put it in the right position. Okay, so last class we ended on this acetoacetic ester synthesis. We're going to talk a little bit today about, and we did talk about these being particularly acidic protons and can be removed with much milder bases. Typically, we will use the ethoxide that coincides with whatever is on this ester group. If you had the methyl ester, you would use methoxide, and if you have the ethyl ester, you would use ethoxide. Pull off that proton and then react with an electrophile through the SN2 reaction to displace the halogen, and you get the alkyl substitution. We talked about this last class. The mechanism is not that difficult. So at the end, though, we do a hydrolysis reaction to get rid of the ester and make the carboxylate. We quench it with acid to make the carboxylic acid. These undergo a particularly facile decarboxylation. We can push the arrows like this where we lose CO2, and we end up getting a substituted acetone. I just wanted to talk a little bit more about that decarboxylation. Someone came up and asked me, and it was a good question, and I thought we would go through it. So this is just showing the bonding changes that occur from these curly arrows that we're showing. So all that's happening is we're forming a bond between the oxygen and the hydrogen. At the same time, we're breaking that pi bond. We break this hydrogen-oxygen bond, make a carbon-carbon double bond, and we break this carbon-carbon bond to make a carbon-carbon double bond there. So our initial products at the instant after that decarboxylation is carbon dioxide and an enol. And don't forget those enols, most of the time, they're in equilibrium with their keto forms, and the ketone is the dominant form in that equilibrium. So that's what actually happens in that decarboxylation. It's born as an enol, but then it just tautomerizes to give us the ketone product. And this is just to remind you that CO2 is a linear molecule, and I just drew it like that because I really just showed the bonding changes there. Good exercise for curly arrows as well is to whenever you see a bunch of curly arrows, just draw on the other side, draw all the atoms in the same places, and then make the bonding changes. Good way to practice. So we talked about it being the synthetic equivalent of an acetone enolate. We would get the same products if we used acetone and a strong base to pull off and make this enolate. We would get the same products. And then we went through a couple of examples. So this part is all just about making the enolate, and we do these reactions sequentially because we can use the mild base. We pull off the proton, we let that reaction go for a little while, then we slowly add our electrophile for the SN2 reaction to get to the substituted acetoacetate. Then we go through that workup to hydrolyze the ester, quench it to the carboxylic acid, and then decarboxylate to get our final product. And we can easily, because the product still has these 2 ketone groups and still has a hydrogen on this proton, we can pull that proton off. This is not quite as acidic because we have an electron donating group that we've added to it now, and quite often we have to use a little bit stronger base. And instead of the ethoxide, we will use T-butoxide, and that's a stronger base and easily pulls that proton off. The equilibrium lies on the side of the enolate. We can then throw in our second electrophile and do another alkyl substitution. And then we can follow it up in the same manner to quench, hydrolyze, quench, decarboxylate. And you'll notice now on a lot of the slides, sometimes I'll talk about these things and sometimes I won't, but I quite often have a little question there. And that's to make you think when you're studying is why does that second proton require a stronger base? Because we've put that electron donating substituent on it, so we've made it just that much less acidic. Oh, I'm going the wrong way. We can also, instead of alkyl bromides as an electrophile, we can use acyl halides. In this case, the reaction is no longer an SN2 reaction. You guys should know the mechanism in this reaction. It was covered in chapter 17. But we still have this nucleophile. It attacks the carbonyl carbon. The charge goes up in the oxygen, and then you form the tetrahedral intermediate, which eliminates the chloride, and you get the acyl substitution. You work this one up in the same fashion, and you notice you'll decarboxylate again, and you end up with the substituted acetone. And in this case, we still have a beta dicarbonyl compound, but we have a beta diketone. The other thing too, for acyl substitution reactions, we can't do it in an alcohol solvent with an ethoxide because then that would just react with our reagent and give us the ester from this thing. So we have to do things slightly differently. We use sodium hydride in a polar aprotic solvent. You guys, aprotic means no active hydrogens that are easily removed by bases. We need it polar because we're having ionic types of chemistry. We need a slightly stronger base because we're in an aprotic solvent and changes the acidity a little bit. Remember, when we talk about acids and pKa's, we're talking about water as solvent. And even when we have very strong acids and weak acids, we're giving an estimate for what it would be in water. And it gets a lot more complicated in other solvents. Acid and base strengths can be quite different. You don't have to worry about that in this course. So we have to use a aprotic solvent. Aprotic because this is a decent enough base and it would pull off a proton on the solvent if we didn't have an aprotic solvent. So we typically use DMF or DMSO. These are DMF. Here's DMF, and this is DMSO. And I've just answered this question, why we use these solvents. We need a polar solvent. These don't have any hydrogens that are easily removed. Although we did do some reactions with this where we used a really strong base to remove one of those protons. It's usually considered aprotic because you need very strong bases to remove those protons. So here's a problem. How would you make the following molecules? Starting with ethyl acetoacetate. You'll notice I'm starting to put a lot of problems in here, and we'll answer these in the tutorials. But I want you to think about them and give them a try so that when you come to the tutorial, you've tried these problems. Some of them will be really easy, some of them will be more difficult. There's another reaction called the Malonic ester synthesis. Notice it looks exactly the same. The only difference is we no longer have an alkyl group here, or CH3. We have another OET group. So this is the ester, the ethyl ester of malonic acid. And same thing. These are going to be much more acidic than normal because of the two carbonyl groups. So the first step of our reaction is the same. We use a base, and we can use a fairly mild base to remove the proton. And we can see that this is stabilized through resonance. That negative charge is shared between the methylene carbon, or what was the methylene carbon, and the two oxygens. So it's a resonance stabilized anion. So this is exactly analogous to the acetoacetic ester synthesis. Everything is the same. We throw in an electrophile and we can do the alkylation. If we want, we can throw in, after that, we can throw in some more base, remove a proton, throw in another electrophile, and get the dialkyl malonic ester. That's all the same. We can do the same thing. We can hydrolyze this. When we hydrolyze it, and then we quench it with acid, and we get a substituted malonic acid. So that's what this is. This is the substituted malonic acid. It is also a beta-keto carboxylic acid. And in fact, both carboxylic acids have a beta-keto group. But when we heat it up, one of those will decarboxylate. The same thing, we'll end up getting the enol-like product from this carboxylic acid, and it will tautomerize to give us our substituted acetic acid. These are the products of these things, these substituted acetic acids. And if we did the dialkylation, everything else is exactly the same. So this is the synthetic equivalent, and it doesn't have it here, but it's really the synthetic equivalent of this. And I suppose they don't like drawing this because you would never see this species exist, right? You would never see this species exist because of this acidic proton. But this is if we could make it, if we could somehow make this and freeze up this so the proton wasn't reactive, this is what the products come from, something that would look like this. So we talk about it being the synthetic equivalent of this or the carboxylate anion, but we end up reacting this carbon with some electrophile and doing either alkylations or acylations on that carbon. So our products are substituted acetic acids, either mono or disubstituted acetic acids. These are just examples, and go through these. Make sure that you understand, and it's exactly the same thing. Base removes a proton, then we throw in our electrophile, and it does either the alkylation or the acylation, depending on what we used as our electrophile. Then we can work it up to hydrolyze and then quench our ester, and followed by heating to remove CO2 to get our substituted acetic acids. So when we have two electron withdrawing groups surrounding one of these, which is the two examples we just saw, we talked about these as being active methylene compounds. There's lots of different active methylene compounds where we have two electron withdrawing groups on either side. It makes them particularly acidic. And we use these quite often in synthesis to make those anions because it's just so synthetically easy to do these things. And here's just a bunch of examples of what we would call electron withdrawing groups. So we can see a couple of examples. Here, this is very much like a beta dicarbonyl compound in that protons here are easily removed because we have this electron withdrawing group and this electron withdrawing group, and we can show the resonance stabilized structures for that particular anion. We talk about that as being the active methylene. And here's just another example of the synthesis we would do. Now this one's interesting. It's actually showing that this would be an SN2 reaction of a secondary alkyl halide. These actually go because we have to have iodine. If we don't have iodine, we'll typically get elimination, but sometimes we can force these and get an SN2 reaction on a secondary alkyl halide. But most of the time, when we do use secondary alkyl halides, we like to use iodine. Hopefully you did that in first semester. Okay, so this is the last real reaction for this, and you're going to have lots of time for your quiz today. The last reaction we're going to do is something called the Stork Enamine reaction, and this is a little bit different. What we're going to do in this case is a reaction we learned in chapter 16. Remember, when we react a secondary amine with a carbonyl compound, we get these enamines, okay? And we get them, the first step of the reaction forms something that looks very much like a hemiacetal, but instead of an OR group here, we have the amino group. And these go on to remove the elements of water and give us an alkene functionality right next to the amine, and we call them enamines. We can think about drawing resonance structures for these enamines. This would be the best resonance structure because there's no charges on it, but we could draw one where we move the electrons like this, and we end up having a positive charge on the nitrogen and a negative charge on this carbon. So this is a nucleophilic site because of that lone pair of electrons. And then when we look at the resonance structure, we find that this is also a potentially nucleophilic site. And if we look at the electrostatic potential map, we see that we have a lot of negative charge density on both the nitrogen and the carbon. So this thing can be nucleophilic in those two positions. And we can take advantage of that. This is not as nucleophilic as an enolate anion, but it reacts much like an enolate anion. We usually have to heat these reactions up, but we can make these, purify them, isolate them. We have to be careful because we have to do it, make sure we're in dry conditions because these are very sensitive to reactions with water to just kick off the amine and give us the ketone back. But when it's in this form, we can put it in a dry solvent, reflux it up with some electrophile, and we can push our arrows, and we can see that we're going to form a bond between this carbon and the carbonyl carbon. Here's our tetrahedral intermediate. We then just kick off the chloride, and we end up with an aminium salt because there's our positively charged nitrogen. This thing is very susceptible to hydrolysis. We just have to throw in some water. We might throw in a little added acid just to make sure the reaction goes, and it just pops that off and puts the carbonyl back in its place. And we end up, these are nice reactions. They're easy to work up. They're easy to clean up because we get this salt. We can get that out in the aqueous wash, and we can get pretty high yields of our alkylated compound. Now, what we could have done was we could have taken the original ketone, reacted that with lithium diisopropyl amide, and removed that proton. But that requires harsh conditions, dangerous reagents. This is a nice, easy thing. This is a reaction we could easily do in an undergraduate lab. So we could do these instead of the very dangerous lithium diisopropyl amide reactions. And we get the same compounds. They can be acylated, alkylated, and used in Michael additions. Don't worry, you don't know what Michael additions are yet unless you've read the next chapter. We'll learn that starting next week. So this is an example. Another example, we make our enamine. We have our electrophile. This thing is a Halobromo ester. Halobromo esters we've seen before. Now, think about it. We talked about active methylene groups. We have an electron withdrawing group here and an electron withdrawing group here. So although those may be acidic, in this particular instance, they can also be very good electrophiles because it's electrophilic because of the partial positive charge character on that carbon. We're used to seeing primary alkyl bromides as our electrophiles. If we put an electron withdrawing group on the same carbon, it becomes an even better electrophile. So these reactions actually go in very high yields. 75% is a good yield for this type of reaction. Same thing, so we do our nucleophilic substitution reaction. They're SN2 types of reactions. And we get our aminium salt, which we then just work up with water and maybe a little bit of acid and get our ketone product. So like enolates, the alkylation reactions are SN2. So we can typically only use methyl, primary, allylic, and benzylic halides. And here I talk about alpha haloesters, and I just told you why they're particularly good electrophiles. For these reactions, take a look when we do the formation of the enamine. We've now put a substituent in here, and we have the possibility of two products. One would be, if we were using enolates, we would get the kinetic product versus the thermodynamic. This would be the thermodynamic product because it has the more substituted double bond. And we talk about this being the kinetic product. This also provides us with a way of favoring the kinetic product without using that dangerous lithium diisopropylamide, which we would have to use if we were starting from the ketone and trying to alkylate it. The reason is these things all get forced, and this one, these all get forced in the same plane, and we end up getting some steric interactions between this methyl group and the methylene group here. So this goes in high favor for what would end up, what we talk about as being the kinetic product. Okay, so we get the less substituted double bond. Then we can clean this up. We can separate these, or we can separate them after, but we end up getting dye substitution on each side of it rather than the thermodynamic product, which would put our alkyl group on this side. So it just provides a method to get the kinetic alkylation product in high yield. Now, here's a preview of things to come, not in this class, don't worry about it, although I want you to think about these things. Let's not forget about stereochemistry. Oh, I must not have saved it. I had these different colors. So there's a number of ways where we can alkylate this, and there's a bunch of potential products. So this one, you can see we have a stereocenter. We can have this product, and if I had, there's an isomer. These are all isomers, but this has an enantiomer, right? So this could be a pair of enantiomers, and we would expect to get a racemic mixture. We can also put the alkyl group on the other side, and it could be either anti to that methyl group or syn to that methyl group. So on the opposite sides of the ring or on the same side of the ring. So those are the three potential products we could get. You could imagine maybe we would prefer one enantiomer over the other. So through the different reactions we've learned, we actually can use, oh, there we go. So what kind of isomers are these? Do you guys remember? What do we call those? Are they enantiomers? Diastereomers. They are diastereomers. This one, we could, if I put the methyl group back there and this allyl group up here, we would have the other enantiomer. So we can't forget about that. We haven't really talked about it a lot, but we provide, through different conditions, we could use a mild base in a polar A product solvent and heat it up, and we could get an alkylation. And that's going to probably give us more of this because this is the thermodynamic product. If we did it in LDA at minus 78 degrees, we're going to get a mixture of these diastereomers. How much of one or the other is going to depend on the relative stabilities of the diastereomers. And we might expect a little bit more of this just because when we form that enolate, there's a little bit of steric bulk there that may stop approach from the electrophile if it were coming from this side. We can also form the pyrrolidine enamine, which is, pyrrolidine is that 5-membered ring with a nitrogen atom in it. That was what we used to form the enamines a minute ago, and that would favor the kinetic product, the blue ones. But we can also use enamines that have some stereochemistry. So form the enamine of this and then try and think about what the products would be. So form the enamine, and you'll see that that should favor one of these over the other, and this should favor the other one over the other. And it becomes fairly obvious why. So we're done with chapter 18. We did more or less 8 reactions, and we did the halogenation and then a special one of the halogenation reactions, which we called the haloform reaction. So that's all of chapter 18, and there are a number of problems that I've put in here, problems like this. So starting from non-deuterated cyclohexanone, can you provide a synthesis for the following compound? Provide the mechanism for the placement of the first deuterium atom. Now normally, how many people know what deuterium is? Okay, deuterium is just hydrogen, but it has, what's different about deuterium from normal hydrogen? It's got a neutron, that's right. So it's atomic mass as 2 instead of 1. So it's twice as heavy. That actually provides us with a lot of ways of looking at different things. So quite often, particularly in medicinal chemistry and in molecular biology, we like to make a lot of deuterated compounds because it provides us a way to probe things. So you'll often see synthesis. The nice thing about enolate is it provides us a way of deuterating compounds in a specific place. So here's another one. So make 2-pentanone. Very tricky problems. You'll have to look up glutaric acid, cyclobutane carboxyl. That's interesting. I had to use that once. I used the cyclobutane carboxylic acid when I worked in industry, like tens of liters of it. It is the foulest smelling chemical I've ever come across. We actually had a little spill in the lab, and a number of people had to run and throw up in garbage cans, like immediately. The stuff is horrible. I couldn't smell for 3 weeks because of it. But once you see the answers to these, they're not so tricky. But they are tricky problems when you look at them. They're the type of problems when you look at them, you may struggle and struggle and struggle. And then when you see the answer, it'll become obvious. So that's a good one to take a look at, struggle with it. Now, having said that, any of you that have textbooks, these are in your textbook. You'll also notice a lot of the problems come from the textbook. And then I grab a lot of these problems for the midterms as well and the finals. So that's it, and we have lots of time for... So the next chapter is going to be chapter 19. What we're going to see is that we've talked about enolates as nucleophiles, but we don't want to forget that carbonyl compounds are good electrophiles. So we're now going to take a carbonyl compound, convert some of it into a nucleophilic compound, and react it with the other ones as an electrophile.